Bismillahirrahmanirrahim. Today we are going to proceed with the second lecture on the course of Advanced Computer Architecture. In our first lecture, we discussed certain fundamentals of computer organization and architecture. We also discussed the concepts of stored program. Later on, we discussed a programming model called ISA, Instruction Set Architecture. Instruction set architecture is a very important and useful model for a programmer who is well versed with machine language and assembly language. He just considers computer as a resource with a set of instructions, the memory address space, and all the registers available along with the CPU. Today, we are going to discuss foundations of computer architecture. You have already discussed the fundamentals of architecture in other courses. We will have a quick browsing through the concepts of computer architecture in order to have a good connection with what you already know. We'll discuss 5 modules in this computer architecture. The first one we'll talk about is the taxonomy or classification of different computers and the instruction sets. Then we will look into the different types of instructions. Finally, we'll discuss the addressing modes, and then after the addressing modes, we'll discuss the RISC and CISC architectures. Finally, we'll see the performance parameters of different architectures. You will see that today's lecture is more broad and it's less deep. After going through these concepts in the later lectures, you will see that gradually we'll have more depth and you will go on getting the feel of the subject in the following lectures. The taxonomy or classification of computers could be done based on the ISA instruction set architecture. In general, we could have 3 classes. The first one we could call accumulator-based machines. The second group is stack-based machines. And the third one is the general purpose register machine. We'll look on all these 3 classes one by one. The accumulator-based machine has an accumulator which is a special purpose register available in the CPU. The accumulator, as the name implies, accumulates or holds the data. This data could be an operand or it could be the result of some operation. Nevertheless, the accumulator is never an addressed register. In the accumulator-based machine, one could say that it is a single address machine. Accumulator-based machine has the advantage that it requires less memory, and the less memory accesses would also be required. It was a time when the memory was pretty expensive and the accumulator-based machine could give an economical solution. In the case of accumulator-based machine, the data is already available, and the other operand, one of the operands is available in the accumulator, the second operand is fetched from somewhere else from the memory, and after the operation the data is further put into the accumulator. The second class is the stack based machine. The stack, as you are already familiar, is a last in first out structure. It could be a structure which could be implemented in memory or with a group of registers. You are quite familiar with this concept. It's just like a stack of plates if you go to a restaurant. The last plate is taken out first, and at the end of the day, the first plate is the last one to be taken out. Exactly the same way, in the case of a stack organization, the push and pop instructions would just take out, read the data as a pop from the top of the stack called TOS, and after manipulating, then the data is placed back on the top of the stack. The stack is also called, the stack organization is also called a zero address architecture. Let us say if we want to add two numbers, then first of all these two numbers would be read from top of the stack, and the next number from the top of the stack, and the arithmetic logic unit, after adding up these two numbers, would push back the result on the top of the stack. Now the third architecture is the general purpose register, generally called GPR. In this case, a number of general purpose registers are available to the programmer in CPU. Apart from these general purpose registers, there are some special registers also available. However, these registers are usually not visible to the programmer. The main advantage of GPR is that registers could be addressed with lesser number of bits. For example, if there are 32 registers, only 5 bits would be required to address any of these 32 registers. Whereas if we need to access memory, then it might be for a byte, then, or depending upon 8 bits, 16 bits, 24 bits, or 32 bits, depending upon the length of the word to be used in programming. To summarize, we say that when we compare the three available classifications, the accumulator and the stack-based machines offer the opportunity to the programmer that intermediate results could be stored into the CPU, and it's not necessary to store the intermediate data into the memory. The GPR gives the possibility of holding the data in the registers. The arithmetic logic unit could pick up the data straight from the registers instead of memory. Therefore, the total execution time may be reduced. To summarize, we have seen three organizations available: the accumulator-based, stack-based, and the general-purpose register-based. Let us now look at the second aspect, and that is the instruction set in a little bit more detail. An instruction needs to convey 4 features. First of all, the first part of the instruction, the functionality would be to tell what to do, like add or move. It could be a data transfer instruction, it could be an arithmetic instruction, it could be a logic instruction. So a part of the instruction which tells us what to do, that is generally called an opcode. The second information which is required to be incorporated in the instruction set is the operands. The instruction would tell from where to fetch the operands. Now, the possible locations of the operands could be, this operand could be available already in the CPU, it could be available in one of the registers, or we need to access it, fetch it from the memory at an address which would be given or indicated by the instruction. Finally, the instruction needs to tell that after performing the arithmetic or logic operation or any other operation specified by the instruction, the result has to be placed in a destination. So the destination address has also to be specified. After specifying the destination address, the instruction needs to point out to the next instruction to be executed. By default, this would be the instruction in queue. In case there is a jump instruction, then the address of the next instruction to be executed would be given by the jump instruction. After discussing the features of an instruction, we conclude that there would be a variable number of addresses required, and these addresses need to point out from where to fetch the operands and where to store the data. Let us now look at the classification of the instructions based on the addresses to be specified. At the most, 4 addresses need to be specified in the instruction. Now, the minimum number of addresses would be 0, and that is as was the case for stack organization. Let us look in more detail the intermediate requirements of the addresses in the instruction. Based on the address requirements, there are 5 classifications of the instructions. The maximum number of addresses to be specified in an instruction is 4, and therefore will have a 4 address instruction. Then we could have 3 address instructions, 2 address instruction, a single address instruction, and a 0 address instruction, depending upon how we specify the operands and the destination. The structure of 4 address instruction would be, for example, 1 byte specifying the opcode. The next few bits would specify the address of destination, and then we will have 2 addresses of operand 1 and operand 2, and the final part of the instruction would specify the address of the next instruction to be executed. However, as we know that if we go sequentially, it is not necessary to specify the address of the next instruction to be executed. So we can chop off this information from the last part of the instruction. Therefore, if we do away with this information, we are left with a 3 address instruction. So therefore, the structure of 3 address instruction would be opcode followed by destination address and the two addresses of the operands, that is operand 1 and operand 2. We could further simplify this 3-address instruction to a 2-address instruction by having a situation where one of the operand already resides in the destination. So therefore, we have a common address specifying the destination address and one of the two operands. So the structure would be opcode followed by an address which to start with would be the address of operand 1, and after the results are received from ALU, this would contain the contents or the result as a destination address. So therefore, the destination address and one of the operand address are common, and we just get, in this case, a 2-address structure. Finally, if we say that we have a 1-address in structure, then the accumulator, as we discussed earlier, would be containing one of the operands to start with and also the final destination. So therefore, implicitly, the second operand would be specifying from where to fetch one of the two operands. So therefore, only one address needs to be specified. The second one is an accumulator where no address specification is required. Finally, the 0 address corresponds to the structure of stack as we have discussed earlier. Now please note in this case that these are the abstractions. The real machines may have any combination of these structures. We could have an implementation with 3 addresses, 2 addresses, or there could also be a situation in between. As we said that the registers would require lesser number of bits to specify, and therefore it is called a half address. So whenever we fetch data from one of the registers in a general purpose register organization, then we could have one operand coming from the memory and one coming from the registers. And this would be an example of what we will call 1.5 register, 1.5 address machine. So in practice, we'll see that we do not have a purely stack machine, a purely accumulator-based machine, or it could be a combination of any of these 3 structures which we have already discussed. Let us now consider an example to illustrate these concepts. First of all, we assume that the opcode is specified by 1 byte in the instruction. That means 2 raised to power 8, 256 different instructions could be specified by the opcode. Secondly, we assume that the addressable memory or the maximum addressable memory is 16 megabytes. This would mean that we need 24 bits to specify any address in the memory, or let us say we have 24-bit address bus. We also assume that the length of the operands is also 24 bits. That means if we need to fetch one of the operands from the memory, we would require 3 bytes. Finally, we say that the data bus has a width of 1 byte. Therefore, 1 byte at a time would be accessed from the memory to the CPU, or in one clock cycle will say the data that we are going to fetch from the memory would only be 1 byte. Now let us have a look at the worked example in the next slide based on 4, 3, 2, 1 and 0 address in the instruction. Now this slide shows the example of 4 address instruction. First of all, the first part of the instruction indicates opcode, the next part destination, then source 1, source 2 and the next address. 1 byte is required for opcode. The destination address is specified by 3 bytes. Similarly, the 2 source operands each require 3 bytes, and the next address is also specified by 3 bytes. If we look at the total code size required for one instruction, that would be 1 plus 3 plus 3 plus 3 plus 3, which turns out to be 13 bytes. Meaning that if we use one 4-address instruction, for each of such instruction will require 13 bytes of code in the program. Now the second important feature which is to be noted is the number of bytes to be accessed from the memory. This ultimately would tell us how fast the program would run. For this example, we need to fetch first of all 13 bytes of instruction in the fetch cycle, then 6 bytes would be required to fetch operands from the memory, and after calculations we put back the data as a destination into the memory, which would need another 3 bytes. So altogether 22 bytes need to be accessed from the memory into the CPU. Similarly, in the next slide, the working for 3-address instruction is given. You will note that now the total code size turns out to be 10 bytes, and the number of bytes accessed from the memory in this case is 19. If we have a 2-address instruction having opcode followed by the destination and one of the source addresses, the total code size per instruction would be 7 bytes, and the number of bytes accessed from the memory would turn out to be 16 bytes. For a single address instruction, similarly, the code size is just 4 bytes, and the total number of bytes accessed are 7 bytes. For a 0-address example, the code size is just 1 byte, and the total number of bytes accessed from the memory is 10 bytes. If we compare all these 5 examples, the summary is given in the next table. The first column just indicates the instruction format, the second column gives the code size, and the next column gives the memory bytes accessed. Now one thing is quite clear, that 4-address instruction requires the maximum code size and the maximum memory bytes to be accessed. Nevertheless, it's amazing that for 0-address instruction, the memory accessed memory bytes accessed are not the minimum. You will see that in the fourth row, single address instruction requires the minimum number of bytes accessed from the memory. So one cannot conclude always that zero address instruction would give us the best implementation. The practical machines are not so simple. The real machines may use 3 address, 2 address, 1.5 address constructs. A very simple way to look at how the data is manipulated is that whether arithmetic logic unit gets or fetches data from memory or from the CPU registers. So we could distinguish based on this criterion and say that we have either both the operands coming from the register, and this would be a half address example. If both the operands come from memory, it would be an example of 2 address instruction. And if one of the operand comes from one of the registers and the other operand is fetched from memory, this would be an example of 1.5 instruction, 1.5 address instruction. Now, a very simple mechanism would be where both operands come from registers. We assume that the operands have been prefetched from the memory. Such machines are called load-store machines. And these load-store machines are mostly the RISC machines, or reduced instruction architecture is based on this concept. So therefore, there is no direct access for ALU from the memory. The ALU gets data from the registers. So therefore, it could be called a register-register machine architecture or a load-store architecture of the computer. Load-store architecture, which is a register-register architecture, is the simplest one. If we get one of the operands from the memory and other from the register, this would be called a register memory or memory register structure. In this case, the address would be 1.5 address construct. Now, if both the operands are to be fetched from the memory, the architecture would be called a memory architecture. In this case, one would require 2 addresses to be specified, and it would be a 2 address example. Let us now look on the example of executing one instruction using different address schemes. Now, this example is an example from your textbook. We need to evaluate an expression A equal B plus C multiplied with D minus E. The table shows 4 different implementations. The first column indicates a 3 address implementation. The second column gives a 2 address implementation. The third column indicates a single address implementation, and the last 4th column gives a 0 address implementation. In the first column, it's quite clear that we need only 3 instructions: an add, a multiply, and subtract. So in this case, we just have a 3 address construct of the instruction. Now, if we restrict ourselves to 2 address in the second column, the number of instructions are 4. Similarly, we have 5 instructions for single address, and the maximum number of instructions are required for 0 address. We have looked on different instructions. These instructions could be classified into 3 different groups. It could be arithmetic logic operations done by the instruction. It could be a data movement in the form of communication with memory or I/O, or it could be a program flow instruction. Let us now go to the second aspect and see how the addresses are generated in the instruction. So we come to discussion of different addressing modes. There is a variety of different addressing modes. To name a few, we could have immediate addressing mode. In immediate addressing mode, the address is not required. Straight away, the data is a part of the instruction. That means that data is available as a part of the instruction. We could have a direct addressing mode. In the case of a direct addressing mode, a constant as a part of the instruction could specify the location in the memory, that is, the address in the memory. Then we could have an indirect addressing mode, where the instruction could, for example, point to a register, which in turn could contain the location of the memory. Or it's not necessary that it is a register. It could be an address in the memory, and that address in turn could contain the address of another location from where data is to be fetched. Then we could also have indexed addressing mode. This is a pretty useful mode when we are dealing with arrays, and arrays could be addressed very nicely by using this mode. Let us look at examples of these addressing modes in our following slides. We start with the example of immediate addressing mode. Data for the instruction is part of the instruction itself. There is no need of any calculation for the address. Only limitation in this case is that the range of addressability is limited. For example, if there are n bits available for specifying immediate addressing mode, then from a reference point we can just address the instructions as -2 raised to power n minus 1 up to 2 raised to power n minus 1 minus 1. We have considered an example as load A 1, 2, 3. The contents of the instruction register are indicated. You'll just see, following the opcode, the data 1, 2, 3 is available, and that would just go in this example to the accumulator. After this particular instruction is executed, the accumulator would contain 123. Note here that we have used load A instruction as an example to maintain consistency and to limit the number of operands to only 1. Next example indicates direct addressing mode. Now load A with square brackets, same data 1, 2, 3. This is just one ASM notation which is required for assembler, other notations could be used. Now in this case, note that 1, 2, 3 is not the data, rather it is the address in the memory. After this instruction is executed, the access would be given to an address in memory indicated by 1, 2, 3. For this example, the contents of the memory are 456, and this would be transferred to the accumulator. The next example indicates indirect addressing mode. Now you see load A with double square brackets. Now the inner brackets indicates that it is now the address of 1, 2, 3, where the address from where to fetch the data would be given. So the address of the pointer is 1, 2, 3. At 1, 2, 3, 456 in this example indicates the address in the memory. So at 456, the data available is, in this example, 789, and that would be transferred to the accumulator. So at the end of execution of this particular instruction, accumulator would contain 789. The next example is the register direct addressing mode. In this example, we just write load A R2. Now, no memory location is involved. The data is available in one of the general purpose registers. In this example, register R2. Following the opcode, the instruction register contains the address of the register from where to fetch the data. In this example, R2. So after execution, we will have in the accumulator the data available in register R2, which in this example is 1, 2, 3, 4. One can notice that the number of bits required for specifying the register is much lesser. No memory access is required. The next example indicates register indirect addressing. Now load A followed by a square bracket containing R1. This means that in the instruction register IR, opcode is followed by address of R1. Now we go to address R1, which indicates 1, 2, 3, and that is the address in the memory from where data is to be fetched. So for this example, the contents of the memory location 1, 2, 3 are given as 456 and would be transferred to the accumulator. So at the end of the execution, the resultant in accumulator would be 456. The next example indicates the displacement addressing. In different books, different terminology is used for this addressing mode. It's also called indexed addressing mode or base addressing mode. For our example, load A with a square bracket contains R1 plus 8. 8 is just an example constant in this case. The instruction register contains opcode followed by address of one of the registers, which in this case is R1, followed by a constant which in this example is 8. After execution, the contents of the register R1 are fetched, which is in this case 120. It is added to the constant 8. Result is 128, which indicates the address of the memory from where data is to be fetched, which is in this example 456. Another example of addressing is the relative addressing, and that is given in this case just as a jump instruction. For example, we say jump 4, opcode for the jump, followed by 4, which means that the contents of the program counter register would be just updated, and in this case the program counter contains 120. The constant following the opcode is 4, so the resultant would be 124, and it would give the next instruction to be executed as 124. This is normally used for short jumps and is called relative addressing mode. Let us now look at two design philosophies in architecture called RISC and CISC. RISC stands for Reduced Instruction Set Computer. The philosophy in RISC is to have the length of each instruction as constant. So it's not a variable instruction. Each instruction occupies a fixed number of bytes. One instruction is executed per clock cycle. Basically, the philosophy boils down to having the load store concept. We assume that in a RISC architecture, the data is available in the registers. It has been already fetched from the memory. So therefore, the load and store are the only two instructions which would give interaction with the memory. Once the data is available in the registers, all other instructions would fetch data from these registers. As a result of simplified instruction set, we get lesser number of addressing modes and simplified instructions. When we say that in the case of a RISC, one instruction per clock cycle is executed, does it mean that after one instruction is executed, we need to wait for the other instruction? It is not so. We could use other concepts of prefetching and pipelining, which we will discuss in later lectures, and see that we could get a better efficiency and even more instructions executed per clock cycle. Let us look into the features of RISC design aspects in the following slides. As we have seen, RISC stands for Reduced Instruction Set Computers. This is a concept or philosophy of machine design and is not a set of architectural features. The underlying idea is to reduce the number and complexity of instructions. New RISC computers may have some instructions that are still quite complex. The main features of RISC machines are that one instruction per clock period is executed. All instructions have the same size. CPU accesses memory only for load and store operations. It is simple and has few addressing modes. The most important feature in RISC design is one instruction per period, per clock cycle. By using speed-up techniques like pipelining, program throughput can be made even better than this, even though the execution time of individual instructions may be longer. All instructions in RISC have the same size, and this is a simplification. Usually, one word or 32 bits is the size of the instruction. CPU memory accesses are only through load and store operations, as already explained. That means that all operands should be in CPU registers at the time when ALU requires these operands. Simple and few addressing modes are used in RISC. With complex addressing modes, complex arithmetic must be performed for address calculations, which takes time. So, as a result, if few and simple addressing modes are used, the time for address calculations is reduced, and that results in simplification for RISC design. There is a much lesser work to be done per instruction in RISC philosophy. That also implies that the clock period T could be reduced as compared to a CISC philosophy, because lesser work per instruction needs to be done. Improved usage of delay slot is implemented. Delay slot is the waiting time for a load or store instruction to access memory, or for a branch instruction to access the target instruction. RISC designs allow the execution of the next instruction during this waiting time. If the program or compiler places an instruction in the delay slot that does not depend on the result of the previous instruction, the delay slot can be used effectively. That needs improved compiler design. Finally, the efficient usage of prefetching and speculative execution techniques could be used. These techniques are used more efficiently in RISC designs. We will see the details of these concepts in a later lecture. The CISC design philosophy stands for Complex Instruction Set Computers. The features corresponding to CISC machines are: a CISC machine can give more work per instruction. Now, this was necessary in the days when memory that is available in the form of RAM or disk was very expensive and slow. This required compact programs with more functionality per instruction. In a CISC design philosophy, a wide variety of addressing modes are available. As an example, 14 addressing modes are used in Motorola Processor 68000 and 25 in MC 68020. Just as an interest, try to find out how many addressing modes are used in Pentium. The length of the instruction is variable, and the execution time per instruction also varies. CISC machines attempt to reduce the semantic gap. Semantic gap, the gap between machine-level instruction set and high-level language constructs. The CISC designers believed that narrowing this gap by providing complicated instructions and complex addressing modes would improve the performance. However, this concept did not work very well because the compiler writers did not find this improvement to be worthwhile and useful. There are some disadvantages associated with the CISC design philosophy. Clock period T cannot be reduced beyond a certain limit because when the capabilities are added in the instructions, the CPU circuits require more execution time, and therefore it's a complex job to do it in a shorter time, and this in turn places a limit on the smallest possible value of T, and hence the maximum value of the clock frequency that could be used in the processor. Complex addressing modes delay operands to be fetched from the memory because of the larger time required for calculating the address. In a CISC philosophy, it is also difficult to make efficient use of the speed-up techniques. These techniques include pipelining, prefetching, superscaling, and speculative execution. We'll discuss these concepts in a later lecture. We have seen that there are two important design philosophies, RISC and CISC. Having a fixed instruction size and limiting the addressing modes, RISC is a better design philosophy and is being used presently for most of the present-day machines. The CISC gives improvement in performance only under certain limited conditions. To summarize, today we have discussed some fundamental concepts of computer architecture. We discussed the taxonomy or characterization of computers and their instruction set. Then we discussed different important features of the instruction set. Finally, we discussed the different addressing modes, and we briefly looked at the RISC and CISC architectures. Next time, we are going to discuss the performance measures of different computer architectures. Till next time, Allah Hafiz.